Hey, dude.
Yeah.
I bet that if we jumped and teleported halfway across the field, that we couldn't make it all the way across.
You mean like a half, and then a quarter, and then an eighth, and then a 16th, and then like a 32nd, like that?
Yeah, dude.
No, you could.
No, you could not.
Yes, you could.
No, you couldn't.
Bet you $5 we could.
$5.
$5.
Okay, ready? 1, 2. Okay.
Halfway.
Yep,
Yeah.
this is halfway.
Ready?
Ready? 1, 2, 3. Okay.
This is a quarter of the way, right?
Yep.
Right. Okay, ready?
Okay.
Ready? 1, 2, 3.
All right.
That's an eighth.
Yep.
Yep, ready?
Yep.
1, 2, 3. That's a 16th.
Look, I know we're getting close, but
Look, there it is. It's right there.
we still have so much to go.
It's right there. It's fine. We'll get
Okay.
there. Ready? Ready? 1, 2, 3.
We're getting close, but
Yeah. Ready? Ready? Go.
A few inches later.
I'm almost there.
you're not even teleporting anymore.
Shh.
You're just
Yes, I am.
hopping
Wait.
in place.
Wait, ready? 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 You know, this isn't right.
No, it's not.
Hey,
Hi.
we're gonna go. Ready?
Okay,
Ready?
yeah.
1, 2, 3.
One eternity later.
Okay, so there must be an easier way to figure this out. On the football field, we traveled 1 unit of distance, then half that distance, then half that distance, over and over and over again. Written out, that looks like this, a series. In the general form, that's 1 over 2 to the nth power, so we'll use that for our sum. Sum of 1 over 2 to the n from n equals 0 to n equals infinity. For this particular sum, we'll use the geometric test, which states that the sum of a series is equal to the first value a over 1 minus the ratio r, so long as the absolute value of r is less than 1. In this case, our ratio is 1 over 2, so it meets the standard. Plug 1 into the equation for a and 1 over 2 into the equation for r, and we get 1 over 2, which is equal to 2 times the initial distance. Because the initial distance was half the field, eventually we would get to the end of the field, but it would take literally forever to get there.
The Greeks were able to prove this thought experiment by drawing a square, and then they would split the square in half consecutively, and what we end up finding out is that the square ends up being infinitely small in one corner. And if the square is infinitely small, it would have no area. This leaves us with one complete whole square.
That's a nice bike you got there.
Oh, thanks.
How far can it go?
A long way.
So, if you went double the distance every single iteration, do you think you could reach a point?
Yes.
I don't think so.
Yes, you could.
I'm looking at that bike and I don't think it'll reach anywhere.
$20.
20 bucks.
$20. I'll travel twice as far as I've gone until I get somewhere.
I don't think you'll make it.
I'll make it. Here we go.
Okay. I'll
You're
see
gonna
you
have
with
to find
20
us that way.
bucks. She's not gonna make it. Did you make it?
No. Am I there? Did it work?
No.
Oh, good.
20 bucks.
Yeah, shut up. Go back.
Okay.
The next day.
Time for math again. So we traveled a certain distance on a bike, doubling the distance each time. Let's use the divergence test to prove that this would never go anywhere. So in this problem, we convert that to a sum which looks like 1 plus 2 plus 4 plus 8 plus 16, and so on. Taking a look at the pattern, we notice that the pattern appears to be 2 to the n, where n starts at 0 and goes to infinity. So as a sum, that's 2 to the n from n equals 0 to n equals infinity. To find whether this series converges, we can actually use the divergence test and take the limit of the general term as n approaches infinity, and see if it converges or diverges that way. The limit of the general term as n approaches infinity in an infinite series only converges if said limit is 0. If it is anything else, it diverges. As observed, the limit of the general term is infinity. Therefore, it diverges, and so the whole series diverges. So,
What you making there, buddy?
Gabriel's cake.
Oh, so like Gabriel's horn with cake.
Yep. And it's done. I bet you I can frost this cake.
No.
No, I totally can.
You can't. Nope.
Nope, I totally can. $5. I can bet this. I can frost this cake.
You're on.
Nope. Ready for some $5?
Do it.
All right.
Wow, that's some nice frosting.
It's vanilla, I think.
Cream cheese, you heathen. This doesn't really look like the curve 1 over x. That's okay.
That's okay. It's just like super zoomed out.
It's cake.
We'll just pretend that there's stuff there. Now I'm not even using the butter knife properly.
Many hours later.
To find surface area using an integral, we use a modification of 2 pi times the radius equation. This gives us 2 pi times the integral from 1 to some number f of x times the square root of 1 plus the derivative of f of x under all of squared dx. We know that our function value is 1 over x. If we take the derivative of this, we get negative 1 over x squared. All we need to do now is substitute these values in, which we get 2 pi times the integral from 1 to infinity, 1 over x times the square root of 1 plus negative 1 over x squared, quantity squared, where 1 over x is the function and negative 1 over x squared is its derivative. Simplified, it is 2 pi times the integral of 1 over x times the square root of 1 plus 1 over x to the 4th dx. Now we are going to prove its divergence using comparison test. We're going to use 1 over x as our test subject. By using the integral test, we know that 1 over x diverges because it is the harmonic series. Here, we are proving that 1 over x is less than our specific function. To do this, we set up an inequality where 1 over x is less than 1 over x plus the square root of 1 over 1 plus 1 over x to the 4th. And now we simplify by multiplying x over and then squaring. This gives us 1 is less than 1 over 1 plus x. Since 1 over x diverges as we just proved earlier, we can conclude that the whole surface area of this function diverges.
I couldn't frost it.
Oh.
$5 is yours.
Oh. That's nice.
Yeah, you're right. I couldn't frost this cake. I'm hungry though. I bet I can eat this cake.
No.
Yes, I totally could.
No, you can't.
Yes, I can.
Okay, $5 says you can't.
$5 says I can.
Do it.
Okay.
Do it.
Ugh, I think I'm gonna throw up.
Dude, that was a lot of cake.
But I did it.
And now I owe you $5.
$5.
Nice.
Thousands of tears later.
To determine whether the volume of Gabriel's horn converges, we find the volume of 1 over x rotated around the x-axis. To do this, we take the harmonic series 1 over n as n goes from 0 to infinity and integrate it with an x-axis rotation. All we need to do then is find the area under its curve and see if it converges by using an integral, more specifically, the integral from 0 to infinity, pi times the quantity 1 over x squared dx. We can simplify by taking out pi and moving the square sign to the denominator, since it's just 1 squared, and we can then solve. Since this is an improper integral, we must use the limit as c approaches infinity. Taking the integral gives us -1 over x from 1 to infinity, all of that times pi. -1 over infinity makes 0, minus a negative gives us 1. 1 times pi is pi, and this gives us the volume of pi, which, as we know now, converges.